Hello, this is going to be a short lecture in physics on collisions. So without further ado, let's get to it. Okay. Collisions. Two things crashing into each other, collisions. Two or more things. In a collision, momentum is conserved. The entire momentum of every collision in every direction is conserved before or after. Now, we know about conservation of momentum before, and we also know that momentum is a vector quantity. So the momentum in one component at the beginning of any interaction has to be the same as at the end, the total momentum. In the north, south, the east, west, or the up and down directions, if you want to think of it that way. Momentum must be conserved in every dimension. If two things crash into each other like they are here, let's look at this. Two things are crashing into each other. M1 is crashing into M2 and they're sticking together. Let's see if we can't solve this problem. We have to find the final velocity. We know the initial momentum, we usually use P for momentum, final momentum. So the initial momentum is M1 V initial. Now, M2 is at rest. So the initial velocity is M2 as zero momentum to begin with. The entire initial momentum is M1 V initial. Now, after the collision, they stick together. So the final mass is just the sum of the two masses. V final. And we have to find for V final, which is just this. No. What's the final momentum after the collision? Well, how about instead of finding the final momentum, we can just find the initial momentum, since momentum is conserved. It's going to be M1 V initial. So that's going to be mass of 12.3 times 10.2 P initial, P final is P initial. If you plug the numbers in, M1 V initial 12.3 times 10.2 is going to be 125 kilogram meters per second. At the initial momentum, it's going to be the same as the final momentum. Now to find the final velocity, we have to use this equation. Again, this comes initial momentum here, final momentum, which are the same. We just move this here. And after plugging in the numbers, we have a final velocity of 3.83 meters per second. Now let's take a look at the problem we did. Notice in this crash, they stuck together. That is called a completely inelastic collision. In a completely inelastic collision, kinetic energy is minimized after the collision. Okay, important idea. Let's do a couple of problems. In completely inelastic collisions. This one, we have a truck crashing into a car going in the opposite direction. So again, for problem one, we have initial momentum equals final momentum. The initial momentum is the mass of the truck, the 3,400 to 6,500. We'll call this mass T, VT initial. Now, notice they're colliding head on. The car is going in the opposite direction. So if we're calling this truck's velocity positive, we have to make the car's velocity negative. Via the car initial, and they're going to come together M truck plus M car times the final velocity. And when we do this, we get a velocity of 6.7 meters per second. You plug in the numbers. Again, we have to divide by this. M truck, your 6,500 plus M car, plus your 3,500 kilograms. And we get this final velocity, which is going to be 6.7 meters per second. Now, number two is trickier. Number two is happening Number two is trickier. Number two is happening at an angle. Erase some of this here. So for number two, we're going to have something like this. The truck is moving east. It's moving this way. And the car going to be a little smaller, moving north, and they crash right here in the middle. And then after they crash, they're going to be together, and they're going to come out at some angle like this, okay? Here they are. Two vehicles crash together, and they come out at this angle. Call this angle theta. Now, so when we are finding conservation of momentum here, it's like this. Initial momentum in the x direction has to equal final momentum in the x direction. I'm going to call the x direction east-west, and the y direction north-south. Now, what's the initial momentum in the x direction? The truck's moving east, so that's going to be the mass of the truck times the initial velocity of the truck and there's nothing else. The car is initially in the north-south direction, the y direction. But the final momentum in the y direction, they're going to crash together. In the x direction, mass truck plus mass car times the final velocity times the cosine of the angle. Now, for momentum in the y direction, we have the mass of the car, this is the north-south direction, times the initial velocity of the car. The truck is going perpendicular, so the truck has no initial velocity in that direction. And that's truck plus mass car final velocity times the sine of that angle theta. Oops. And now we have a system of two variables and two equations. I would do these first by dividing them and get the tangent of the angle equals this equals mass car initial velocity of the car dividing mass truck over initial velocity of the truck, and then take the tangent. Put that in your calculator. We have theta equals 34 degrees and then we can take this, plug this into either of the equations and find the final, either of these equations and find the final velocity of the car truck system, which is 27 meters per second. Of course, it's going to slow down a lot after that. They're going to crash and then go off into the ditch. Okay, but let's say the velocity is right here after they crash. If that sounds going unrealistically fast, two vehicles crashing together. Moving on. Now let's talk about elastic collision. In the elastic collision, kinetic energy is conserved. They crash into each other and bounce off. That is different from an inelastic collision. A 3.34 kilogram object moving at 16.1 meters per second crashed into a 7.5 kilogram object at rest. Find their final velocities if the collision is completely elastic and the collision is elastic. Well, for the first case, we just have M1, what we've been doing, V1 initial, equals M1 plus M2, V final. And of course, these equations are based on initial momentum here and final momentum. And V final, this gets moved to the denominator here, okay, to find V final. And V final going to equal, when you after you plug all these numbers in, .08 meters per second. Now, if the collision is elastic, they're going to bounce off each other and conserve kinetic energy. We have M1, we have an equation for momentum here, M1, V1 initial. Now M2, again, the velocity is still initially 0, but they're going to bounce off each other this time. M1, V1 final, plus M2, V2 final. This is, of course, initial momentum, and this is final momentum. Well, it's an elastic collision. We have kinetic energy to worry about too. So if we remember the formula for kinetic energy, it's 1/2 mv squared. So remember, this is kinetic energy, EK. K or EK, EK. This is an elastic collision. EK initial has to equal EK final. So initial, we just have 1/2 M1. Again, 0 kinetic energy for M2 since it's initially at rest. V1 initial squared equals 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. Okay, now when you plug in these numbers, We have a system of two variables, two equations. We have two variables, V1 final and V2 final. And we have a momentum equation and a kinetic energy equation. Two variables, two equations. It's a little tricky. When you plug the numbers and solve for these, we have V1 final equals negative 5.94 meters per second. And V2 final $10.2. Now what's the negative sign mean in this context? Velocity is a vector quantity. It's moving, this 3.34 kilogram object is moving towards another object. It crashes into it and bounces off. It's moving in the opposite direction of it that it originally was. Now that's how you do an elastic collision. We're not going to do any right now, any elastic collisions in 2 or 3 dimensions, because that gets very complicated, okay? But you would need, if you were to do that, you would need 3 variables, 3 equations. You would need 2 momentum equations, since momentum is a vector quantity, and 1 kinetic energy equation. And kinetic energy is a scalar quantity. Now let's talk about elasticity of collisions. In the real world, you will never have perfectly elastic or perfectly inelastic collisions. A car crash is never going to be a perfectly elastic collision. The energy goes into smashing the car, so it's obviously losing kinetic energy, but it doesn't mean the two vehicles will just stick together. So it will not be. So this car crash on the picture, like real collisions, are neither perfectly elastic or perfectly inelastic. Now, we have to use this formula for the elasticity, K. It's the difference in final velocities over the difference in initial velocities between two objects, and it's in absolute value. Okay, so this K value is always positive. And you can do this, you can set up both of these to be positive or both to be negative. It's the absolute value. Okay? K is 1, the collision is elastic. And then K is 0, the collision is completely inelastic and kinetic energy is minimized. Here are the conditions, the collisions we can have. Super elastic. Kinetic energy is larger after the collision, an explosion. Elastic. Kinetic energy is conserved. And inelastic, kinetic energy is smaller after the collision, K less than 1. That's what most collisions are. Or completely inelastic, the two objects stick together, kinetic energy is minimized. Now, a jargon watch, in problems, inelastic might mean completely inelastic. Okay, it depends on the context of the problem. But if it's inelastic and they don't stick together, it's still not completely inelastic, if that makes sense. An as a matter of jargon, an inelastic collision can mean both of these conditions. Okay, so be careful for terminology and always look for context. A basketball of mass 624 grams is moving at 11.2 meters per second collides with a football of mass 430 grams moving at 6.3 meters per second. After the collision, the basketball is moving at 10.7 meters per second, and the football is moving at 10.1 meters per second. What's the elasticity of the collision? Again, K, the elasticity. It's going to be the difference in final velocities, which is going to be 10.1 and 9.7. Over the difference in initial velocities, which are 11.2 and 6.3. And I get K in this equation. I get K is 0.082. That's not very elastic. That's almost completely inelastic. Probably those balls, I would say both the basketball and something like this happen in the real world, I'd say both the basketball and the football need to be pumped up. Now let's look at this. A car of mass 3,500 kilograms moving at 23 meters per second rear ends another car of mass 4,500 kilograms moving at 12 meters per second. So how fast is the 3,500 car moving if the velocity of the 4,500 kilogram car is 19 meters per second after, and this is after the collision. So for this first one, 2A, again, start with conservation of momentum. The initial is P final. M1, V1 initial, plus M2, V2 initial. And they are both going to be positive in this case, since they are both moving in the same direction. M1, V1 final. M2, V2 final. Now this might look confusing, but we actually know everything here except V1 final. This is just a simple linear equation. And when you solve for it, you get 14 meters per second. Now to find the elasticity, the difference in final velocities, 19 minus 14, over the difference in initial velocities, 23 minus 12, and the answer 0.45, which is actually really elastic by the standards of a car crash. Okay, I hope that was an interesting introduction to collisions, and thank you very much. And all right, I hope this was what you were looking for, and I would be honored to come join you at your institution next fall. Thank you very much.